The title of this presentation is Towards a Robust Distributed Framework for Election Day Voter Check-in. This work is conducted at Augusta University, Georgia, jointly with Ahmed Alarud, Kostas Bush, Rich DeFrancisco, Derek Kowalski, Greg Murray, Nisha Panwar, Reza Rahamer, Edward Tremel, Jay Heslin, and Craig Albert, presented by Alex Schwarzmann. This work is supported in part by the National Science Foundation's Secure and Trustworthy Cyberspace Award. The electoral infrastructure is a massive distributed enterprise supported by four different components: voter registration systems, election management systems, voting terminals themselves and ballot marking devices, and the voter check-in processes implemented as pollbook solutions, all working in concert. The first three areas received a lot of research attention in recent years and have been widely studied. The check-in process until recently has been a manually supported process, but the electronic help is on the way. Or is it? This diagram is from our paper in the IEEE Transactions on Information Forensic and Security that shows the overall activities surrounding an election in the United States. The election involves, of course, the voters, the election officials, a number of systems, and audit processes before, during, and after the election. I'm not going to go through this diagram in detail. Focus is only on the red box showing voter check-in. Before a voter can vote, they need to be checked in. And so if the rest of the systems are perfect, but the voters are not correctly checked in or not allowed to be checked in, the whole election is in trouble. What is the purpose of electronic poll books? On the election day, before a voter can cast their vote, they need to be checked in. The purpose of the check-in process is to ensure the one voter, one vote guarantee. That is, that each eligible voter is enabled to vote and that they vote at most once. Typically, this process is manual and it involves extracts from the voter registration databases, and then poll workers manually check in voters and then cross their names off the list, thus ensuring that they vote only once. This process is known to be laborious and error-prone, and there are documented cases of issues on the election day, ranging from opening delays, long lines, errors, as well as potentially disenfranchising numerous voters who otherwise should have been eligible to vote. Thus, nationally, there is a growing demand for electronic solutions for the check-in process to address all of these deficiencies. As is the case, commercial vendors rushed to offer hastily constructed electronic pollbook solutions, and a number of states deployed these solutions, and the general situation is that there is a massive premature deployment of immature systems. As I already mentioned, several areas comprising the electronic election enterprise received substantial attention from the researchers, some of them from our own community, and yet a crucial component, the check-in systems, received surprisingly little attention from academic researchers. In 2018, the National Academies of Science formed the Committee on the Future of Voting, and I had the privilege of presenting at one of the meetings. And following that, the National Academies issued a report titled Securing the Vote, Protecting American Democracy, where they warned about serious risk in deploying poorly designed electronic poll books. It is important to note that electronic poll books are complex, dynamic, distributed systems, and it is non-trivial at all to ensure their correctness, security, integrity, fault tolerance, flow balancing, performance. And this area deserves a lot of attention from our research community, and this is one of the reasons I'm presenting this to you now. Elections are an essential part of any democratic society. Today, elections are conducted with the help of electronic systems, and it is important to note that all, without exception, electronic voting systems that were independently examined were found to contain serious vulnerabilities in the areas of security, integrity, and reliability. Why is this the case? Following the multi-billion-dollar federal investment in the upgrade of election systems, most vendors rushed to develop such systems, and they have substantially underestimated the challenges in building these systems to be robust and dependable. These problems can be traced to the divergence from or the complete obliviousness of established results in algorithmics, verification, crypto, distributed computing, and sound engineering practices. What we're observing is a complete dislocation of theory and practice in the space of electronic election systems, and electronic poll books are not immune to this. Even considering the very modest goals that are pursued by commercial developers of electronic poll books, these relatively simple systems already suffer from a variety of issues. First of all, there is no absolute guarantee of one voter, one vote. Many systems have a window vulnerability where if somebody is fast enough, they just may be able to vote more than once. Some systems rely on central servers or the internet, and that is an obvious concern. All of them use unhardened commercial off-the-shelf components. It is unclear what are the fault tolerances of these systems and what guarantees do they provide. The systems suffer from poor data integrity checks. Voter lists are not authenticated. Licenses, the barcodes on driver's licenses used for identification may contain issues that the systems are not able to deal with. The performance claims are not clear. It is far from obvious how these systems can scale in terms of being able to support voters when the voter turnout is high. The use of crypto is very poor in communications, opening these systems for various remote attacks, and the systems use wireless communication, which makes them open to denial of service. For example, one can purchase a few $100 jammer, place it outside the polling place, and the election just may come to a screeching halt. The list of deficiencies in commercially available systems is quite long, and I'm not going to go through it in detail in the interest of time. In recent years, several states took efforts to define reasonably formal requirements for electronic poll books. We have participated in such efforts in New England in particular. Well, what should be an adequate e-poll book system? Well, first of all, it must have an absolute one voter, one vote guarantee. The system initially contains a list of voters. As the voters check in, they are able to vote, for example, given a ballot. The system must be able to deal with high voter turnout, and so it must support concurrent check-in and also implement load balancing between the devices. Thus, the system really needs to be dynamic. Individual check-in devices must be able to be introduced during the election, and the faulty devices need to be removed, and suspicious devices must also be isolated from the system. Clearly, the system needs to be fault tolerant, having no point of single failure. And so the good news is that the system is inherently redundant because there are multiple check-in devices, but taking advantage of that is important to make the system fault tolerant. And of course, redundancy introduces the challenge of consistency, and that is a difficult problem. So the data store needs to be clearly survivable and support concurrent access and consistency. And last but not least here, many algorithms that implement various features for fault-tolerant systems do not say what happens when the limits on fault tolerance are exceeded. So if more than the designed number of components fail, well, the system does not guarantee anything at all. And this is not adequate in the current setting. There must be a recourse that would allow for the election to go on, possibly with the help of election officials, even if fault tolerance limits are exceeded. As we have seen already, many E-pollbook implementations, if not all, suffer from a severe dislocation of theory and practice. In particular, vendors make naive claims regarding the features and guarantees of their systems that are completely oblivious of the well-established, some even venerable results in distributed computing. I'm sure most of you know the majority of the results listed here, and I will spend in the next few slides a few moments on each of these results, placing it in the context. As you have already heard, commercial E-pollbook solutions do not guarantee absolute consistency. On top of that, they also imply that they are able to tolerate crash failures without specifying any limits. In some cases, even implying that as long as one check-in system remains active, the system can operate. Well, this flies in the face of a very well-known result, where that even for a static system, you need to have a majority non-faulty components to tolerate failures. Vendor solutions attempt to guarantee agreement in the operation of their systems, but at times fail to have a common operating view, which is so important in making sure that we have the guarantee of one voter, one vote. For a more comprehensive solution, the agreement problem that is known to be very challenging in distributed systems is needed, for example, to introduce a new check-in device and to handle high voter turnout, to remove an unreliable or compromised device, and to agree on the status of a particular voter, whether they voted or not. And again, vendors are oblivious to the fact that this is a difficult problem, generally speaking. Coordinated action with link failures is one of the venerable challenges and problems in distributed computing. Vendor implementation of E-pollbooks are silent on what happens when communication is disrupted. And in some instances, they are not able to recognize the fact that during the absence of communication, or when messages are lost, a particular voter voted twice. It is well known that providing availability, consistency, and partition tolerance in a distributed system is a challenge, and this challenge even leads to some impossibility results under specific circumstances. Vendor solutions typically do not even realize that partition is a possibility, and are able to proceed, not realizing that something is wrong, and the result being that voters that attempted to vote twice will be able to do so, and what is worse is that the system is unable to recognize this. By now, it should not be a surprise that vendor solutions appear to be oblivious of the venerable FLP result regarding reaching agreement in the presence of crashes and asynchrony. In particular, the vendor claims that imply that they're able to agree on the status of faulty devices in the system, or the claims that maintain that voter status can be consistently maintained despite failures, these cannot be taken seriously without additional substantiation. For example, why FLP is not relevant in the particular implementation, or what additional assumptions are made that allow these systems to circumvent this impossibility result. Reaching agreement and maintaining consistent state in the presence of malicious failures is even more challenging. In this space, vendor solutions do not even admit the possibility of any device in the system exhibiting nefarious behavior. They assume that all components are good team players, and yes, they may fail now and then, but nobody ever takes a malicious action. And this kind of an assumption is very simplistic. First of all, let us realize that outside of the election, some components collect dust in a closet somewhere for 360 days. And what happens when one of these devices is tampered with or is simply stolen? You know, these devices may be intentionally or accidentally activated on the election day, and what happens then? Also, the individual components of an E-pollbook system are very often commercial off-the-shelf devices, and they're just as prone to acquire virus or get malware as any other commercial systems. And so it is extremely important to consider malicious behavior when implementing dependable electronic pollbooks. The requirements for electronic pollbooks imply that these systems must not only be distributed, they also need to be dynamic. One of the reasons for advocating electronic pollbooks is that these systems will be able to reduce voter wait time when the voter turnout is high. This can be accomplished by introducing fresh check-in devices when the lines are long. So, an electronic pollbook system must be able to reconfigure on the fly when new devices are introduced, and of course it must be able to remove misbehaving or crashed devices from the configuration and also isolate suspected devices from the system. Reconfigurable dynamic distributed systems is an attractive area of research, and electronic pollbooks is a perfect target for applying research results to real systems. A comprehensive electronic pollbook solution is a technological solution for a problem that needs to be responsive to legal requirements and societal needs. Our project thus encompasses three interwoven dimensions: social and political science, computer and cyber science foundation, and system implementation and evaluation. It is interesting that in recent years NSF introduced computer science research programs that require the participation of social, legal, or political scientists. Our research in this space is in fact funded by one such NSF program. In this presentation, I will not be talking about social and political aspects of our research. Instead, I will focus on more relevant theoretical and systems issues. Distributed computing community has already, as you have seen, produced relevant results, but much work remains. In this context, threat and failure models need to be better understood, as well as the role of humans as active participants in the computation, especially when failures occur beyond the design parameters of algorithms and protocols. Electronic poll books are mission-critical systems, and the dynamic data store supporting this application need to be better studied. Given the one voter, one vote imperative, research on at most one's semantics is immediately relevant. A rigorous approach to distributed audit logs is an interesting area, and here blockchain technology has a meaningful application. You did want me to say blockchain at least once, right? Also, how do we deal with situations when too many failures occur? That is, the number of failures that is beyond the theoretical bounds. Here, a self-stabilizing approach can be explored under the direction of human actors. Last but not least, cybersecurity concerns must be integrated in any solution from the get-go. In the systems implementation and evaluation dimension, our goal is the provision of a reference implementation that incorporates the results of our research and deals with challenges inherent in any such complex system. It is important for the practical implementation to showcase our theoretical results and show how they address the requirements placed in such systems. The framework requires rigorous approach to authentication of software components, devices, communication, and for encryption of relevant information. It needs to include machine learning-based intrusion detection component, and otherwise sound engineering techniques need to be introduced to deal with standard cybersecurity requirements. Finally, the system needs to be evaluated with the help of election officials and test voters representing broad segments of the electorate. Thank you for your attention, and I will be glad to answer your questions during the live presentation. I hope this presentation convinced you that there are fruitful areas of research that can directly and immediately benefit the needs of a democratic society and its electoral processes.